Hello class 10. In the last few classes we have discussed about current, resistance, resistivity, potential difference and all. So far we know that current flows through a metallic conductor. But what actually motivates, what actually supplies energy to the electrons to flow through the metals? The element that supplies energy to the electrons to flow through the circuit is called battery or a cell. That you know, in your house you have a battery or a cell around it. So now what is there inside the cell which motivates the electron to flow through? Battery actually supplies energy to the electron to flow through a circuit, and we have a technical term to that. The term related to that is called electromotive force. Electromotive force, the definition is, it is defined as the energy spent or the work done per unit charge in taking a positive charge around a complete circuit of the cell. Okay, that is the circuit outside the battery as well as inside the cell also. Whenever we are having suppose we are having a simple circuit consisting of a cell and a resistance, external resistance connected around it. Now positive charge flows from this side to that side, and actually the electron flows in the opposite direction. That energy that is stored in the battery, energy per unit charge, which is used up by the electrons to overcome the external resistance as well as to complete the path inside the cell, is called electromotive force. Electromotive force is the energy per unit charge in taking a positive charge around a complete circuit of the cell. In other way, EMF can be defined in this way also. When no current is drawn from the cell, that is when cell is in the open circuit, the potential difference between the terminal of the cell is called the EMF. EMF, as you can see, that EMF is the work done per unit charge. EMF is equal to work done per unit charge. It is similar, it will have the same unit as that of potential difference. So EMF has a unit volt. Okay. Now, actually what is this? What is this EMF and how is it used up? To understand this, when electron, or let's say when the charge flows through a circuit, work is done, a part of that work is done to overcome the external resistance, and part of the work is done to overcome the internal resistance of a cell. What do you mean by the internal resistance of a cell? When charges flow through the battery, the path is not so easy. The battery also applies certain resistance to the charges. That resistance offered by the battery is known as the internal resistance. And what are the factors on which internal resistance depends upon? The factors that affects the internal resistances are: number one, the surface area of the electrode. You can just relate it to the external resistance, the factors on which external resistance depend upon. Surface area of the electrode, as the resistance depends upon the, inversely depends upon the area. So here also, larger the surface area of the electrodes, lesser is the internal resistance. So internal resistance depends on four factors. First of all, internal resistance is denoted by small r. Internal resistance depends on the surface area of the electrodes. Internal resistance is inversely proportional to the surface area. The first factor there in case of the resistance was the length of the wire. Here also, internal resistance depends on the distance between the electrodes. It's directly proportional to the distance between the electrodes. The third factor in case of resistance was temperature of the resistor. So as the temperature increases, the resistance was increasing in that case. Similarly, in case of internal resistance also, as the temperature increases, internal resistance also increases with temperature. Now, what was the fourth factor in case of resistance? Fourth factor was material of the conductor. Similarly, here also, the internal resistance depends on the nature and concentration of the electrolyte. It depends on nature of electrolyte. Okay. Now, so let me draw a simple circuit here and try to understand how the EMF can be correlated, how EMF can be correlated with internal resistance. So, we have our simple circuit here consisting of a cell, and we draw the internal resistance of a cell like this. Keep this in mind. Internal resistance is taken to be in series with the equivalent resistance outside the cell. If the outside resistance is R, then the internal resistance is, if the internal resistance is small r, then these two resistances are considered to be in series. And let us consider the EMF, here is E. Then we can say that, and if I current flows through it, E is used up, this is the total work done per unit charge, energy stored per unit charge. It is used up to do the work to overcome the external resistance, and to overcome the external resistance, the potential drop will be, according to Ohm's law, is equal to V is equal to IR. This is V, and to overcome the internal resistance, the drop across the internal resistance due to the internal resistance will be I into small r. Okay. So when the battery is operating, we cannot measure the EMF of a cell. We can measure the EMF of a cell if the cell is not operating. Then how can we measure? If the cell is not operating, how can you measure? In the higher classes as you go, it will come across a circuit, come across an experiment where we'll measure the EMF of a cell. That we'll discuss later on. As of now, EMF is equal to V plus IR. So when the battery is operating, a part of the energy is used up to overcome the internal resistance. The remaining part, that is the V part, is used for the external circuit. This V part is known as the terminal voltage of a cell. When a battery is operating, if you put a voltmeter or multimeter here, you measure the terminal voltage, subtracting this drop due to the internal resistance from EMF. So V is equal to EMF minus IR. This is your terminal voltage. Okay. Yeah. Now I have a question 1 for your assignment, this week's assignment. My question is, suppose so far we are talking about the resistance through a uniform cross section, a wire having uniform cross section. So what will be the flow of current? How will be the flow of current affected? How will the flow of current be affected if the cross section is non-uniform? Now the question is, once again I repeat, if the cross section of a wire is non-uniform, how will the flow of current be affected? Will it be affected or remains unchanged? Okay, that's the question. That's your question number 1 for assignment. Yeah, let us now move on to a few numericals from your exercise. Question number 11. A wire of 9 ohm resistance having 30 centimeter length is tripled on itself. What is its new resistance? So first step to solve the numerical is to note down the data. In the first case, the wire resistance of the wire is 9 ohm and the length of the wire is 30 centimeter. Immediately convert it into meter, 0.3 meter, and let the area is A. Now in the second case, what did they ask for? The length of the wire was 30 centimeter. Okay, the length is tripled on itself. That means it's folded on itself. Okay, so first time folded, then second time. So tripled on itself means what is the new length becomes? What is the length of the new wire? The new length is 10 centimeter, that is 0.1 meter. In the second case, resistance is unknown, length is equal to 0.1 meter, and as we fold it on itself 3 times, the area becomes, new area becomes 3A. So here we get the equation. What is the working formula? R is equal to rho L by A. Here we get 9 is equal to rho into 0.3 by A, and here we get R dashed. This is our equation 1, and R dashed is equal to rho 0.1 by 3A. Rho remains unchanged because it's the same material. So this is your equation 2. Now we divide equation 2 by 1. Equation 2 divided by 1. What we get? R dashed by 9 is equal to rho 0.1 by 3A into A by rho to 0.3. So we get, rho is cancelled, we get this equal to 1 by 9. So what is the value of R dashed? R dashed, we are getting R dashed is equal to, transporting 9 to this side, 9 by 9 is equal to 1 ohm. Okay, this is one question from your book. Now my question, second question for your assignment is, please listen to me carefully. Suppose you have a wire of resistance R and length L. Suppose you have a wire of resistance R and length L. If the wire is stretched to triple its length, what will be the new resistance? Suppose you have a wire of length L and resistance R. If it is stretched to triple its length, what will be its new resistance? Okay. Then let me move on to one more problem. Question number 8 here from exercise 8A. Let me read out. 2 wires of same material and same length have radii R1 and R2. Radii R1 and R2. 2 materials, 2 wires of same materials. Compare the resistance. Let the resistance of the first material be R1 and second one be R2. Compare the resistances and resistivity. Because these two are made up of same material, both of them will have the same resistivity. So the ratio of resistivity equal to rho by rho, that is 1:1. Okay, now this is for the second part of the problem. Now coming back to the first part of the problem, what is the ratio of the resistance? So in this side, let me find out the area of this R1, the material 1. Area, cross-sectional area A1 is equal to pi R1 square. Here the cross-sectional area is pi R2 square. So here the resistance R1 can be written as, because the lengths are same for both the wires, R is equal to rho L by pi R1 square. R2 is equal to rho L by pi R2 square. So what will be the ratio? R1 is to R2. We get, dividing this by this, as R2 square by R1 square. Okay, that's all for today. There are 2 questions I have asked in this session. You have to answer me within a day. Thank you so much.